Professor Pete Smith, and I hope you enjoy the session. Thank you very much.
Thanks very much, Nicole. Right, so today I'm going to talk about, do we need to remove carbon dioxide from the atmosphere to tackle climate change? Next slide, please. Oh no, I can control them myself, can't I? Here we go. Yeah, so this is a slide showing possible futures. So at the little yellow line at the top shows the business as usual trajectory of greenhouse gases that we're currently emitting into the atmosphere. So we're still continuing to emit them. This annual growth is continuing to grow, and under business as usual, if we don't do anything to change our ways, our greenhouse gas emissions might not peak until about 2060, and that will put us on this line, this yellow line at the top, which would leave emissions at round about what they are now by the end of the century, and this would push our global temperatures up way beyond safe limits. So we're looking at maybe 3 or 4 or 5 degrees Celsius increases in temperature, which would be absolutely devastating for humans, human health, ecosystems, and a number of coastal areas and small island states would be underwater by the end of the century. So this is not a future that we want to live in. So what was proposed under the Paris Agreement, the Paris Climate Change Agreement in 2015, was to try to limit our emissions to get us on track to below 2 degrees Celsius, with every effort to try and achieve limiting our global temperature rise to 1.5 degrees above pre-industrial levels. So that 2 degree line is shown here on the red line. That shows us where we need to be. We need to be at net zero emissions in the second half of the century. Now, to hit the 1.5 degree target, which I've not shown on here because it would make it all too complicated, we need to hit net zero by round about mid-century. So that line comes down even faster. So the thing to note is that we have to not only stop emissions, but we have to change the direction. So rather than increasing them, we have to cut them by around about 4% per year, every year until 2050. So this is a real big challenge. What's shown in the colours on the right hand side is the green area there that you can see. This is what we could achieve by conventional abatement technologies. These are things like renewables, nuclear, and the decarbonisation of our transport, for example, by using electric cars with energy generated from renewables. So these are the sort of things, these are conventional abatement technologies, which means that we don't emit so much CO2 into the atmosphere. But what you can see from that is that doesn't get us to net zero. It just takes us down quite a significant chunk, but it doesn't get there. That's because in the brown section, we still have some emitting technologies. So this includes things like agriculture, which emit methane and nitrous oxide, 2 potent greenhouse gases. And with the best will in the world, we can't reduce those to zero because this is a biological system and you can't control everything in biological systems. So if we want to feed ourselves, which of course we do, then we're still going to have some emissions in the mix from agriculture and maybe other sectors, very difficult to abate sectors, such as some forms of heavy industry, aviation, if we don't manage to develop hydrogen aircraft quick enough, and some other technologies. So what that means is that if we have to reach net zero, because we got some positive emissions on one side of the graph, we need some negative emissions on the other side of the graph. So this is greenhouse gas removal, and that's shown in the blue line, the blue area below the axis. So we'd use those negative emissions, removal of CO2 from the atmosphere or other greenhouse gases, to balance those emissions that are still in the mix from things like agriculture and maybe aviation and heavy industry. So that's why we call it net zero, because it's net zero because it's a balance between some negative emissions and some positive emissions, which even if we've done everything we can to reduce emissions really aggressively and really quickly, we'll still have some in the mix. And that maybe could get us to a situation where we're at net zero. And as you know, the UK has a target for net zero by 2050. And that's divided up differently between the devolved administrations, the different countries of the UK. And Scotland's target is 2045 for net zero. So we're aiming to get to this line of net zero by 2050. And that means that we need to reduce our emissions in the blue line. We need to minimize those emissions that are in the brown band. And we need to have some negative emissions, greenhouse gas removal, if we're to achieve net zero. So I've already answered my question, so you could switch off now if you like, but I'm going to go into a little bit more detail about how we achieve that. What options are available for greenhouse gas removal? So on the next slide, this is a chapter that we wrote for the United Nations Environment Programme Emissions Gap Report in 2017. This is looking at the sort of things that you can use for greenhouse gas removal. On the left-hand side of the panel is the area shown in green are the natural climate solutions. So these are the ones that involve manipulating biology. So it includes things like afforestation and reforestation, so that's planting trees. It includes things like biochar. It includes things like soil carbon sequestration, and it includes things like managing the land, managing peatlands and wetlands to reduce emissions and to sequester carbon, to lock up carbon from the atmosphere. So there's those natural solutions on the left. They tend to be less costly than the engineering solutions. They're closer to deployment. We know how to plant trees and manage the soils, but they are more vulnerable to reversal. Trees don't last forever. They can burn down, they can get attacked by pests, and you can lose all that carbon that you previously stored. On the other side, shown in grey, on the other side of the picture, are the technological options. So these include things like direct air capture, which I'll speak about in a moment, accelerated weathering, which is using rocks that naturally absorb CO2 to absorb CO2, and some ocean-based approaches. So, for example, ocean alkalinity enhancement is a mechanism by which you make the ocean more alkaline because it's acidifying because of the carbon dioxide being dissolved in it. So you could make it more alkaline and at the same time lock up some CO2 from the atmosphere. And then, of course, we can use CO2 into durable products by capturing the CO2 and forming it into useful long-lived materials. But I'm not going to go into the ocean-based approaches and the others and the durable carbon here. The technological or engineering solutions tend to be more costly. There are greater research and development needs, but when you've got the carbon locked up, it tends to stay there, so it's less vulnerable to reversal. And in the middle is a technology called bioenergy with carbon capture and storage. That combines really a technological and a natural component, because you grow energy crops. That's things like trees or miscanthus, which is a very fast-growing grass, which locks up lots of carbon as it grows, and you then capture that carbon when you burn it for energy, and you pump it back underground, and you can store it there for a long time. So this is a combined natural and technological approach. So what I'll do now is I'll just go through and expand upon those, describe each one in a little more detail. So first off, it's important to note that these natural climate solutions, the one in green on the last slide, have quite a large potential. So this was a study that was put together by Bronson Griscom and colleagues in 2017, and it looked at all the options to remove greenhouse gases, carbon dioxide predominantly, on land using land management. So there are forestry options, for example, reforestation, planting trees where they once grew, improved forest management, improved plantations, and other things like forest management. But some of those, like the avoided forest conversion and reforestation, give us very large technical potentials for greenhouse gas removal. So these units are petagrams of CO2 per year, or another way of looking at it is they're gigatons, which are thousands of millions of tons of carbon dioxide. So where we're looking at that number reaching up to 10, that's potentially 10,000 million tons of carbon dioxide per year removed by large-scale reforestation. There are other options in agriculture and grasslands, and predominantly around improving rice management, improving livestock management, and improving cropland management. And then there's also the wetland peatlands option, where we restore and avoid converting our coastal wetlands and our peatlands, which are very large stores of carbon. So let's look at them in a bit more detail now, focusing first on the natural solutions and then moving on to the technological solutions. The first one is planting trees, and this is the most obvious one, I think, to most people, because everything that you see in a tree, all of the biomass, all of the tree, all of the leaves, all of the branches, everything in the tree is actually made of carbon. It's about 50% carbon by weight. And all that carbon has been sucked up from the atmosphere. It doesn't get any of the carbon from the soil. It gets all of that carbon from the atmosphere. So that's shown here as a process, CO2 in, that in arrow, through photosynthesis. Photosynthesis is the process by which carbon dioxide is fixed into the tree, and that tree biomass, as it grows, goes up and up and up, and as it's getting larger, the CO2 in the atmosphere is declining by the same amount. Now, some of that CO2 is lost back into the atmosphere through respiration, because the tree has to live and it's processing all the material, so some of that CO2 is lost, but some of it is fixed. So whenever you see a tree that's grown a little bit more each year and it's getting larger and larger, that is CO2 being locked up from the atmosphere. Better still, some of that carbon in the plant debris and the root materials accumulate in the soil organic matter, so it can also increase the carbon in the soil as well. So any carbon that's locked up in the soil or in the tree is locked up out of the atmosphere, so it's a form of greenhouse gas removal. Coming to soils, there are with soil carbon sequestration, it's really a mass balance equation, so that the more carbon you add to the soil, the more carbon is stabilized, because only about 10 to 15% of carbon that you add to the soil as organic matter is stabilized in the soil. The rest of it, like with trees, like with respiration, is lost to the atmosphere through respiration. So for every 100 kilograms of CO2 that you put into the soil, you retain about 15 kilograms, and about 85 kilograms goes back to the atmosphere. So you can by managing the soil better, you can increase the amount of carbon that's stored in the soil, for example, by changing tillage practices, by changing crop rotations, and by putting residues back onto the surface of the soil rather than taking them away and burning them. So this is another way of sequestering carbon. The third method is a sort of natural solution, but it also includes a technological component. You get biomass, which you grow as trees or grasses in the same way as you do for bioenergy. You then put them through a process called pyrolysis, which is just burning them in an oxygen poor environment. And what this does is it burns them and creates a sort of char material called biochar. It looks not dissimilar from charcoal, but it's different in a number of its characteristics. But there's a photo here at the top right of the slide which shows you all the different forms that biomass looks like, so that it can look like any range of these products depending upon what you've used to create the biochar and the temperature that you've used for pyrolysis. But you then apply that to the soil as shown in the bottom picture. That's biochar applied to soil. You plow it in, and this can increase. This is quite long-lived, quite a long-lived product, and it increases the amount of carbon that you retain in the soil, which is stored as biochar. And the last one is peatland. The last natural one, I should say, is peatland wetland restoration. So peatlands store twice as much carbon as all the world's forests. So it's a really huge store of carbon. But they occupy only 3% of the global land area, but they store 30% of the global soil carbon. So when you restore peatlands and wetlands, what you do is you switch off a large CO2 source. When you drain the peatlands, when they've been mismanaged and drained, they start to oxidize, and a lot of that carbon is lost to the atmosphere. As many at this sort of latitude in Scotland, over 30 tons of carbon dioxide per hectare per year. So that's a hectare of peatland that's been drained emits more carbon than several family cars driving for the whole year, doing about 12,000 miles a year. So that's a huge amount of carbon to be lost. So when you raise the water table so that they're no longer in a drained condition, it switches off that huge pulse of CO2 that's going to the atmosphere every year, and eventually, when you've restored the peatlands enough, they can start to gain carbon again and actually remove CO2 from the atmosphere. And that's why we hear a lot about peatland restoration as a climate solution in Scotland. Moving on to the technological solutions, there's something called direct air carbon capture and storage, so DACS or DAC, which uses a clever engineering solution. So things like sodium hydroxide and amines are two chemicals which naturally absorb CO2. So you have a system where you can pass lots of air over with a fan over these reactors, which contain either sodium hydroxide or amine or some other sorbent. It absorbs the CO2 from the air, so the air comes out the other end of the machine having the CO2 removed, having had the CO2 removed, and that CO2 you can then compress, liquefy and pump it back underground. Or you can, as is being done in Iceland, you can pump it down into basalt seams, and the basalt absorbs the CO2 and mineralizes it so that it's no longer in a gaseous form, it's in a mineral form where it can stay for thousands or tens of thousands of years. So this is direct air capture, and it sounds very attractive. I'll go on to some of the limitations in a moment. So the second part of the carbon capture story, as I said on the last one with direct air carbon capture and storage, the same applies with bioenergy with carbon capture and storage. And what's shown on this big industrial photo here is a carbon capture and storage plant. One is being planned just north of us at Peterhead and at St Fergus. So there are two CCS plants either in development or in planning phase, where the CO2 can be captured and pumped back underground. In this case, this is biomass. So we grow trees, as you do for biochar or as you do for afforestation. That takes CO2 in from the atmosphere, as I mentioned for afforestation earlier on. You burn that biomass and you produce energy. So that's energy that you produce without burning fossil fuels. So that's already a bonus. But then you can capture that CO2 without it going back into the atmosphere, and you can put it into these sorts of facilities, and you can pump it back underground into geological storage. So this is known as bioenergy with carbon capture and storage, or BECCS. The last one that I'll talk about is the technological solution is enhanced weathering of minerals. So this is an example for silica rocks. This is the example for olivine. It's a rock that naturally occurs, and over geological time, it's gradually exposed by weathering to the surface, to the atmosphere. And when it's exposed to the air, it naturally absorbs CO2. So what you can do is you can mine these rocks, dig them up and grind them very small so that you increase the surface area, and then put them out, either apply them to soil on farmlands or woodlands, and they naturally absorb CO2 from the atmosphere, and they can also act as a sort of a liming agent to make the soil more fertile. So this is a great option for both removing CO2 from the atmosphere and for improving the fertility of the soil. So those are the sorts of options available. There are a really wide range of options. anything from as simple as planting trees through to these highly technical solutions such as enhanced weathering and direct air carbon capture and storage. And the potential is very large. So our greenhouse gas emissions currently are around about 50 gigatons of CO2 per year. And you can see that some of these options have the technical potential to offset maybe 10 gigatons of carbon dioxide per year. So maybe about a fifth of the greenhouse gases that we emit, we could potentially, with the technical potential, we could potentially take that CO2 back out of the atmosphere. But there are limitations. So things like cost, land, energy and water requirements and other non-greenhouse gas climate effects, which I'll go into in a little bit more detail now, because it's worth noting that these technical potentials are much reduced when you take into account all of the limitations. That's why we can't rely on greenhouse gas removal to solve our climate change problem. So this is a complicated slide, but what it's showing is the impact of different greenhouse gas removal options on, for example, in the top left, the effect on land, the effect on water, the effect on nutrients, the amount of energy that you need to do it, and the amount of dollars that you need, the cost of these different technologies. You can see that some like bioenergy with carbon capture and storage or planting trees uses a lot of land compared to direct air capture and enhanced weathering, which don't compete for land. Similarly with water, the biological methods are much more use more water than the direct air capture and enhanced weathering, these engineering solutions in the middle. In terms of nutrients, it can require quite a lot of nutrients and you can have negative albedo effects. So that's just a way of saying the amount of energy that the Earth's surface absorbs, that can be changed by large-scale tree planting, for example, which could change the amount of radiation that we reflect back into space and make the Earth warmer through that way. But the biggest differences are in the energy that you put in and the cost. So some examples here, like bioenergy with carbon capture and storage, it's below the zero line, so you actually generate energy from using these solutions, whereas the technical solutions, direct air capture and enhanced weathering, actually use a lot of energy. For direct air capture, you use a lot of energy from pumping the CO2 underground, and also from the scrubbing the carbon dioxide from the sorbent that you've used, the sodium hydroxide or the amine. And for enhanced weathering, most of the energy cost is in grinding up the rock very small. That can be quite an energy intensive process. And associated with the energy use is the cost. Direct air capture and enhanced weathering can be quite costly compared to the other options, the biological options, which tend to be cheaper. So when we put this all together, I tried to put this together in one horrible figure, which I'll go through briefly. What we've got on the bottom axis is the energy. So over to the right hand side of the zero line is the energy requirement. So anything that's far over this side is using a lot of energy. So this is direct air capture up here, which is using a lot of energy. And enhanced weathering is also using energy compared to the other options. The options over here are producing energy. So bioenergy with carbon capture and storage is producing energy, so it has a negative energy cost. And things like biochar and soil carbon sequestration have a very low, they're pretty neutral in terms of energy. Biochar creating maybe a little bit of energy. And shown up the left hand side is the negative emission. So this is like the technical potential that we've seen on the other slides. So BECCS, bioenergy with carbon capture and storage, and direct air capture have the largest potential to remove CO2 from the atmosphere on a yearly basis. A smaller potential for biochar, soil carbon sequestration and enhanced weathering. And of course, afforestation and reforestation It depends how many trees you plant. If you try and plant a huge number of trees, it requires, you can get quite a large carbon removal, but with fewer trees, then you're back down to closer levels to soil carbon. What's shown in the colours is the land requirement. So this purple here, for the very large areas of trees, is showing a high land requirement for planting trees and for bioenergy with carbon capture and storage. What's shown by the size of the circle is the relative cost. So the big circles are expensive, like direct air capture. The small circles are relatively cheap, like soil carbon sequestration. And what's shown in the droplets, the only intuitive thing on the slide, is the amount of water that's used. So some of these have a very low water requirement. Some, like Bex, they use it as quite a high water requirement. And afforestation, trees obviously require a lot of water to grow, so it has quite a high fresh water requirement. But this shows that there's no magic bullet. No one option is the best option, because those that have limited drawbacks have a relatively low potential. Those that have the greatest potential have various drawbacks, either in terms of land or energy or other water use or other things. So we can summarize this on a slide, just showing this sort of traffic light system, which is showing the cost, the energy requirement, land, water, non-CO2 greenhouse gases, and at the end we've just shown the technological readiness. So some options, like planting trees, have just about a clean bill of health. It's pretty green all the way across, but it can start interfering with land. The use of other lands like peatlands and wetlands is usually quite a good option all the way across. Biochar can have a large land requirement. Soil carbon restoration is a really good option because it doesn't really have any negative effects and it's very technologically ready. Things like BECCS and DACS, that's bioenergy with carbon capture and storage and direct air capture, either has a cost disbenefit or a land disbenefit or a water disbenefit or others. And accelerated weathering are less well developed, so they occur. They're problematical because we need more research and development to get them to market. So we've got lots of options available for greenhouse gas removal, and we do need them. We do need greenhouse gas removal if we're to achieve net zero. But as society, we have a choice of how we do that. Do we go down a technological route? Do we try and use nature to help us with that, trying to shape our natural systems so that they're also good for biodiversity, but can also sequester carbon? Or do we have a mixed approach where we use a mix of both? So in summary, I'll just summarize by saying that we failed to act on the knowledge that we need to drastically reduce greenhouse gas emissions for too long. That's why we're in the situation that we're in now. If I was giving this talk 20 years ago, I could have said we don't need greenhouse gas removal, we don't need to remove CO2, but we've continued emitting greenhouse gases into the atmosphere knowing that we shouldn't for too long now, and we've now reached a situation where we need greenhouse gas removal to get us on target to 1.5. To meet 1.5, we do need to remove CO2 from the atmosphere. So that was the provocative title, was asking the question. I'm answering it now. We do need greenhouse gas removal. But these can only complement rapid and aggressive greenhouse gas emission reduction. We can't replace it. So we can't just sit back and say we can continue with our fossil fuel addiction. We have to, as I showed on that green bar in the second slide, we have to drastically reduce greenhouse gas emissions by about 4% per year every year between now and 2050 if we're to hit net zero. But in addition to that, we also have to have negative emissions. It's a vital component of our net zero ambitions, and the time for action is now because we run out of road. I'll leave it there and I'll take any questions.
Thank you so much for that. That was so interesting. I didn't have any idea for today how many options there were. You know, there's so many that it's I'll ask a quick question before we kick off with the chat questions. Yeah. Kind of two questions. What do you think personally is the most viable option, but then also what do you think is most realistic that countries and governments would actually implement?
Yeah, I think that we need a mixture of all measures, because I don't think we yet know which. We're like at the start of a race, and we've not seen which horse is pulling away in the front. So we'd be stupid to place our bets now. We should put a little bit of money on all the horses and see which one pulls ahead. That was the same with wind and solar 20 years ago. Who would have known that they would have come down in cost so quickly and actually be cheaper than fossil fuels now? So we didn't know which horse to back then, and we're in the same situation now. The attractiveness of using natural solutions, the nature-based ones, is that we can also, if implemented correctly, we can use them to improve biodiversity as well. So in areas where we're impoverished in terms of woodlands and forests, we can plant up native woodlands, for example, which would be great for biodiversity and also lock up some CO2 from the atmosphere. So we can look for those win-win benefits, whilst at the same time doing research and development to make these other technological options less costly and use less energy, so we can do more R&D on those ones.
That's great, thank you very much. Just before I start reading out the questions in the chat, just to remind everyone how they can participate. If you haven't done so yet, just click on the little purple icon at the bottom right hand corner of your screen, and you'll see the little speech bubble icon. If you click on that and type in your questions, that will read them out for you. But we have got a couple sitting already, so we'll start there. And the first one is, what about the amount of energy that will be emitted to mine and finish these rocks? Are they readily available, and is this a cost-effective way?
Yeah, so that's the big drawback of the enhanced weathering solution, where you're using rocks, because that's the big energy cost, is in grinding up the rocks and mining them in the first place. Luckily, there's lots of aggregates that are dug up for road building, and the size of particles that can be used for enhanced weathering are no use for road making. So at the moment, there are lots of quarries around the UK, for example, which have huge mounds of waste product, which they consider a waste, which could be used for enhanced weathering. So when we have to go and start mining the rocks from scratch, that becomes very expensive. But we could at least use the waste streams from the aggregate industry to apply that material, and then of course you're just getting it as a byproduct of something you have to do anyway, and that makes it more cost effective. So I think it can be an effective option, but if we had to mine all of the silicate rock all around the world just for the purpose of doing enhanced weathering, I think it would be too costly. It would be prohibitively costly.
Thank you very much. The next one is, what about kelp farms for absorbing CO2?
Yes, I haven't spoken at all about the ocean-based approaches. So that's a blue carbon, they call it a blue carbon solution. So you can use things like kelp beds, or you can use seagrasses to absorb CO2. So these are sort of nature-based solutions that can be used, and they would have fitted alongside afforestation and others. It depends what you do with the material that you grow. If you just leave it there growing, at the bottom, in the case of seagrasses, you just leave it as a seagrass bed, then that carbon is a carbon stock. Even though it's the grass is dying and regrowing, you've got more carbon there than you did at the start. If you're extracting it and then using it, unless you're capturing the CO2, then that carbon is just going to be recycled. So it's not really long-term sequestration unless you're locking that carbon up in long-term products. Like for trees, that would either be standing in the trees, living, out in nature, or it would be harvesting those trees and putting them into long-lived products, like using them in construction in buildings where they can last for hundreds of years.
Super, thank you very much. And the next question is, are there downsides to mass geological storage of CO2? Will that cause problems in the future?
So I would say no. I think there's a lot of worry about CO2 being pumped underground, but it goes down really, really deep. I mean, I didn't realize. I saw a scale model of this, that photo that I showed from Japan. I went to visit that one, and it goes down 1.5 kilometers. And when I saw it to scale, that is such a long way, and there are so many layers of cap rocks over it that there's very limited chance of that escaping back into the atmosphere. And a lot of the places that you're putting the CO2, the reservoirs, are depleted oil and gas reservoirs anyway. So they've been storing oil and gas for 300 million years, So you're just putting it back into those same reservoirs which we originally extracted the oil and gas from. So I think it's fairly safe, and it should be a long-term solution. Of course, it should be monitored to make sure that you don't get escapes. But to date, I think there are 10 large-scale demonstration projects, and so far there's been no large leaks of CO2 from them.
Great, thank you very much. The next question is, can you explain geological storage in the case of CCS?
Yeah, so I just have really. That was why. Well, I've answered that, but I'll just say a little bit more if you like. Geological storage. Well, there are two types. The first one is the one that I've just described, where you pump it back into either saline aquifers. That's aquifers, sort of like underground water that's salty, underground salty water, and you can pump it into those. You can pump it into depleted oil and gas reservoirs. So we've got all the oil out. There's a big hole under the North Sea, and we put it back in that big hole and cap it so that it can't come back out. A really ingenious one that they're using in Iceland with direct air capture. They're using renewable energy, hydrothermal energy from the volcanic activity. They're using that energy to direct air capture, so it's energy free, it's fossil fuel energy free anyway. They're capturing the CO2 from the atmosphere, and they're pumping it back underground into the basalt, because it's basaltic rock in those volcanic regions. And in a matter of months, that gaseous CO2, that CO2 has been mineralized and locked up into minerals, so long-term storage. So that's the other form of geological storage that you can use. You can pump it into basalt seams and have the CO2 stored in that way.
Great, thank you very much. Are there plans to do the same with methane and other GHG that are much worse than CO2 for global warming?
Yeah, so for nitrous oxide, it's not so easy. So that nitrous oxide is 300 times more potent than carbon dioxide. There are one or two things in development for nitrous oxide, but it's much easier to not emit that in the first place. So things like changing fertilizer management practices by not over fertilizing our soils is the best way to reduce nitrous oxide emissions. So there's a lot of low tech solutions that we can do there, which wouldn't compromise agricultural yields, but would greatly reduce the amount of N2O. For methane, that's a very short-lived greenhouse gas, but a very potent one. So at the moment, it's being proposed that we just convert that to CO2. When you oxidize methane, that's CH4 is the chemical symbol. You oxidize it and it goes to CO2 and water. So you convert it to carbon dioxide. The problem with that is that it's a less potent greenhouse gas, but then you've added one molecule of a long-lived greenhouse gas to the atmosphere. So that's the current solution for methane, but I think it's a short-term solution, not a long-term solution, just to convert it to CO2. It would be better if we could capture it some way and turn it into something else that was more durable.
That's great, thank you. I'm going to split this next one into two sections. So greenhouse gas emission reduction. Does this not need a government commitment to, for example, make all new houses have solar power sources, heat pumps instead of gas boilers, etc.? Increase commitment to help older houses use less energy, encourage more green energy, e.g. wind turbines. It seems to me that a lot more could be done now.
Yeah, I agree. Yeah, totally agree. Yeah, all of those things are on the list. They're all on the list of recommendations from the Committee on Climate Change to the UK government and to the Scottish government. We are ramping up our renewables, but we need to do so much more quickly. We need to be really ambitious because, as I said, we've run out of road. Our emissions need to peak by 2025. What's that, 3 years away? And that, we're in serious trouble if we don't manage to do that as a planet. So all governments of the world should be encouraging those things. I really don't think the urgency has been fully understood.
Absolutely. And the next part is, might some technological solutions, for example, making oceans more alkaline, have unintended consequences? How would this affect natural habitats?
Yeah, so yeah, there's that. There is a potential for that. So that's a problem. The reason ocean alkalinity might be better than some of the other options is because the oceans are already acidifying. So a lot of the coral bleaching that we see on the Great Barrier Reef, for example, well, part of it's due to pollution, and part of it's due to ocean acidification. Because as we put more CO2 into the atmosphere, more CO2 is absorbed into the sea, and it forms a weak acid, carbonic acid. So the sea's gradually getting more and more acidic. So ocean alkalinity is a way of both addressing the acidity problem in the sea, and also maybe for locking up CO2. But the question is motivated by, could it have unintended consequences? And I think the answer is yes. So it'd have to be trialed on a very small scale, and have to be monitored very closely before we started thinking about messing with things like that. When you plant a tree, you know where the tree is, right? So you know that's there, and it might burn down or whatever, but then you know what's happened. If you're messing with the sea, it mixes up, and you could have all sorts of unintended consequences. So I would be more nervous about that than I would about planting trees, for example, or kelp beds.
Yes, definitely. The next one is, you hinted that hydrogen is the energy of the future. Can you comment on transition from oil and gas and blue hydrogen, please?
Yeah, so ultimately we need to have green hydrogen. So that's hydrogen that is generated entirely from renewables. So the main way of doing that is through electrolysis of water at the moment, using renewable energy as the source. So that has to be the ultimate goal of where we go. What's being proposed at the moment is the oil and gas industry have expertise, and they have raw materials to do hydrogen from methane reforming. So it's using fossil fuels to produce the hydrogen, and that doesn't really get us very far as a solution, because it's still using fossil fuels basically to generate the hydrogen. So you might as well. Some people say, well, it would just use the fossil fuels in the first place. It's just an excuse to continue using fossil fuels. The argument against that is that it is a transition fuel, and you need enough hydrogen to develop the infrastructure. Nobody's going to make a hydrogen car or a hydrogen bus or hydrogen lorries, trucks, if you can't get the hydrogen to use in them. So the idea is that we maybe use this as a transition period for a short time to build the infrastructure, to build the learning so that we can learn as we do, to get our hydrogen infrastructure off the ground, and we could then gradually transition that to green hydrogen. But that's where we need to be in the future, and the sooner we can transition to entirely green hydrogen, the better.
That's great, thank you. The next one is, what is your reaction to the move to increase nuclear energy solutions? This doesn't seem wise to me.
Yeah, well, it is a low carbon solution. So there's a if you look at the carbon footprint of the energy that's produced from nuclear, most of the energy is produced, you get a bit from the cooling, and most of it's in the concrete and stuff that's used to build the reactors. But that's quite small over the whole life cycle of the plant. So in terms of reducing greenhouse gas emissions, to be entirely objective about it, it's as good a solution as renewables, apart from it being more costly. I would ask the question, since nuclear is so expensive, and since renewables are now cheap, the kilowatt of energy that you produce from offshore wind, onshore wind and solar is now cheaper than that of fossil fuels, and a lot cheaper than nuclear. Why aren't we doing more to step up those renewables? So I'd rather use renewables and build in solutions to deal with their intermittency, because the wind's not blowing all the time, the sun's not shining all the time, through energy storage, maybe even using electric vehicles as electric vehicle batteries as a large scale distributed storage system, which we could use to balance the energy needs. So from a climate perspective, greenhouse gas perspective, nuclear's okay, but getting locked into that, I think is potentially unwise.
Thank you very much. Yes, the same person's commented exactly. Nuclear also seems to have huge potential to be risky.
Yeah,
I think that's, well, you've still got time. If you've got any more questions, anything else you want to get in the chat, please feel free. As I said, you've still got time to answer any other questions that you potentially have. And of course, if you think of something afterwards, we can share that with Pete for you and get you an answer to that. Something pops into your
Ping me
head.
an email.
Yeah, yes, if something pops into your head later on, you can easily do that. So I think that is it. I don't see anything else popping into the chat. So I would just like to say a huge thank you for your time, Pete. It's fantastic, so interesting, and I think really demonstrated the urgency of this situation for everyone that was watching, which is really important.
Great.
So thank you so much, and thank you to everyone who logged in and joined us today, especially since if you're based in Scotland or anywhere near Aberdeen, it is a glorious day. So thank you for coming and sitting in front of your computer for a little while. And I'm sure when we do more online events in future, we'll definitely be asking you back, Pete, to do another session for us. So thank you very much.
Great.
And thanks to everyone who
Thank
attended.
you very much.
Take care,
Thank you.
everyone.
Bye.
Bye.